started. So welcome to our Keen at South Dakota Mines seminar. This week we have Dr. Jim Brenner, who's from Florida Tech, and he'll share with us a couple of things about his own career, but some work that he's done with Keen to develop some expertise, some materials, and some community of practice about making students better makers. So let me hide my video and hand it over to you, Jim.
Okay.
So you can go ahead and share your screen.
Okay. I'm going to talk today about what is a post-disciplinary engineer and how I became one. What you're seeing in the background is a SpaceX launch from not far from our campus. I'm sure that Pierre La Rochelle, if he's there, remembers them well. And I'm going to start out by defining what I mean by a post-disciplinary engineer. Most people are familiar with the concept of an interdisciplinary engineer. I consider that person a jack of a bunch of trades and a master of at least one, but that person probably has either some skill set or some mindset gaps that are keeping them from doing some projects that they would like to do. And so what I'm going to ask you to do, I'd like you to think about what projects have you wanted to do that either a lack of skill set tools, a lack of equipment, or a lack of a mindset prevented you from tackling some of those truly game-changing problems. And was it your own deficiencies or those of your students? And what precisely caused you not to pursue them? And what if I were to tell you that you could get up to speed pretty quickly? And so this is going to be the interactive part of today's talk. Did any of you want to share anything about what you would have liked to have done or would like to do that you haven't been able to get to because of one of these challenges?
Are we talking strictly in academia or just any challenge?
I can hear somebody vaguely in the background.
We might need to go up to.
I'm a student here at Mines. I was just wondering if you're talking about strictly in academia or in any facet at all.
Either. That's a great question, and I like your shirt.
Oh, thanks. Yeah.
One of the ultimate artist makers.
So I have a big problem with like mindless scrolling on my cell phone. So
distraction.
Yeah, I wanted to remake the original BlackBerry, but have it like way dialed back so that it only does like email, text message, like that kind of stuff, but still is like useful in the modern era where we have like QR codes that give you menus at restaurants and like the technology stuff that we need to stay like relevant. And I guess my overall goal is to do it completely from scratch, find some processor, find DRAM, and I guess my lack of knowledge base is the electronics engineering to put those all together and make them work.
It's certainly doable. I call my maker class my inventor's class.
Yeah.
So if you want to learn how to invent things, then today is the start of you going down that path.
Cool. That's my example.
Any other people care to share anything?
Well, I'll jump in. I think along the same lines, I have some ideas for stuff, and it's like I think I can make one of them, right?
Yeah.
But then how do I make a bunch of them, right? Like like there's the like feasibility and funding, like the idea of how to manufacture it at scale and then bring it to market, right? And that's all sorts of resources, right? Time,
It is a
money,
resource
right?
constraint.
Yeah.
Certainly, that is something that I have struggled a little bit with. I've succeeded at times, but I will say that that was not easy. I do, uh, I have started 3 small companies, 2 of which have been quite a while ago when I was only on the technical side of. But in 2020, right at the beginning, I started an ultraviolet disinfection company that did pretty well, and I was both chief technical officer and the major investor. So it is possible, and some of the things that I learned through Keen certainly helped in that respect. Okay, I'm going to switch back to my slides here. And so hopefully that gives you a little bit of a motivation for what's going to happen today. The first few slides here, I'm going to go through pretty quickly with regard to most of my early career. I am a nanotechnology person, and that is at the interface of all of these different fields. So I've had to be a jack of many trades and master of a few.
Hey, Jim, if I could interject just for a second, if you can make the slides in presenter view,
this one?
that would help. Yeah, there you go. Great, thank you.
Got it. So to make anything nano, you need to surround it with a barrier of charges. And some of you have seen this next slide here before with regard to the current entrepreneurial engineering network. On my next slide, I'm going to talk a little bit about curiosity and creating value, and later on about connections. Now, when I talk to people about nanomaterials, there are 4 types: porous materials, nanocomposites, nanoparticles, and coatings. But with regard to all of them, people use their curiosity to discover the scientific principles that form the basis for the engineers to maximize the surface area to volume ratio and thereby create some value for their customers. I've been in charge of a nanotech miner here since 2010 and have been teaching nanotech courses since 2001 and a nanotech lab since 2004. When I started this, there were only 6 undergrad nanotech miners. We still have more labs than anybody else. There's a freshman nanotech lab that's frankly open to any year, but the reason we got the money was because we said we could have freshmen achieve it. A couple of upperclassmen courses for juniors, seniors, and graduate students, a materials characterization 3-credit lab, and a nanotech lecture. And we're different in that we have the students do the lab first and the lecture second, because that's how everybody I knew learned how to do it. For quite a few years, we had people that were getting $70,000, $75,000 a year jobs, but a couple of them were interviewing for $100,000 a year jobs, and I was like, wow, that stunned the heck out of me. And I found out from them that they would have gotten those jobs had they known how to build the equipment. And so back in 2019, I created a new course that I call the Basics of Making. Think of it as kind of like what junior design ought to be, although certainly a first year maker course, we could do quite a few of these things. And so I kind of look at this Basics of Making class as a capstone class for my nanotech minor program. I've done a little bit of everything in my career. I started out in all sorts of energy related projects, realized that I was dealing a lot with nanomaterials and clean energy for the most part. And in a few slides, I'm going to talk a little bit about a company that I was part of that was successful for a while, but unfortunately, I had to sell it. And it was because I was losing customers who wanted freebies. I didn't want to beg the government for dollars. I'm at the very fortunate position now that I can self-fund my own research. And because I had to sell a very profitable company, I had to make a pretty radical career change. And because of that, I needed to address a lot of the questions that I asked you earlier, because I wanted to get into a new field of what was then 3D printing and bioprinting. And eventually I became an expert in tissue engineering. The company that I helped started in a 2-story garage, like this one with Steve Wozniak and Steve Jobs at Apple. And the people that were involved are shown here. The reason I want to talk about this one is that it's a great story. The guy on the right, Alvin Chernikowski, invented the plasma arc reactor at age 19 in Cold War Poland, but he didn't make money on it until 2006 to 2008 when he joined us at Florida Syngas. And this plasma arc reactor, you've probably seen the movie Back to the Future and the Mr. Fusion. He invented that. Now, what was the problem with that? They shouldn't have put the can into the plasma arc reactor. The beer and the banana peel were fine, but shouldn't have put the can in there, because whatever you put in there, you ionize and gasify. And if you put metals in there, it would have some environmental complications. That because we had a patent on what I'll call the low power version of this technology, we did not ionize, whereas our competitors did. We were able to process all of these different fuels that you see here on the far left, glycerols, waste vegetable oil. Mostly we processed municipal solid waste, or MSW, and we made a lot of the products that you see down at the bottom. And for some of those companies, we made them a lot of money. For example, this biofuels company in Peru, they were making 25,000 metric tons per month of biodiesel, and we sold them one of our plasma arc reactors, and they had enough leftover glycerol after powering their plant that they were able to make a decision as to what they were going to make. With the rest of it, they decided to make urea fertilizer. It was enough to fund, actually it was enough for the entire fertilizer business for all of Peru. And so, yeah, we processed all sorts of nasty things, chicken poop, dairy cattle poop, and converted them into energy. Was kind of a break-even business, but chemicals, we made 20 to 30%. I wanted to be one of these guys that I saw on The Men Who Built America, but my dream of becoming one of those titans was broken. And the reason it was broken was because then candidate Obama decided he was going to fund my solar energy competition. And I said, I can't compete with free. So I had to make a radical change in my career. And I asked myself the questions that I asked you at the beginning of today. And so I said, how am I going to do that? I needed to get past some of my own self-imposed limits. but also many of the ones from my students. I was frustrated that students would come to me and say, you know, I don't know how to do this. And I'm asking them, well, didn't you learn that somewhere? And they said, no, we had never learned that anywhere. And then they'd come back in a couple of weeks and tell me, yeah, but I don't know how to do this either. And I said, I need to come up with a way to condense all of these skills that we expect our students to know into one 3-credit class, so that not only is it going to be more productive for us in mentoring them, but hopefully will boost our research capabilities out as a result. And so what I'm hoping to ask you is, what is holding you back? We talked a little bit about this before. Keep thinking about that and ask yourself what's precisely causing you not to pursue them. Okay, I showed this slide earlier. I'm going to talk very briefly about connections that I had made in my own research. And this is from a slide that came from my materials characterization lab class. And I noticed that my small particles of the crystals that you grow from kids, the crystal growing kits, they started lining up into these linear structures, then they condensed, then they started forming crystals. And I realized, you know, some of the Alzheimer's proteins that my friend Xiao Waju was looking at had the same sort of behavior. And then all the way back to my postdoc, I realized, wait a second, all of these materials, whether they be inorganic or organic, actually had something in common about how they self-assemble. And so I realized that if I make these connections, how do I teach my students to also make these sorts of connections? And it was at that point that I got involved with the current Entrepreneurial Engineering Network. And I realized that I was already doing many of the things that they wanted us to do. But what they did help me with was to realize that research is a lot like jigsaw puzzle solving, great works of art, my nanotech, and even life itself. This is from a talk by Rainin McClanahan, who's since joined the Keen staff. And he had this interesting little graphic that you see with the red squares here. The red squares represent lack of information about a certain field. And I realized that people like me that were starting new fields up, we were able to see the big picture when 40% of it wasn't obvious. And we needed to teach that to people that needed to be able to see almost the entire picture. If you look here, you'll see that what I'm pointing to is at the Fashion Institute of Technology, not Florida Institute of Technology. They're our FIT competitor, I suppose. And I realized that what we had been doing with regard to research, we weren't going about solving research problems the right way. No, we ought to take a vastly different approach. The way most people approach it is they find one little square on this and they spend their whole career trying to solve that one square instead of looking at the entire field and trying to solve vast swaths of it at once. And it was at about that time that I started getting involved with 3D printing. We used to have a build your own 3D printer camp. And one of the campers there, now she's at the Lunar Soils Lab, and her roommate, the two of them decided that they were going to convince me that I should offer this new maker class. The one that I'm pointing to now, she said, we have wearable sensor embedded spacesuits. This one that she had just designed went up on Elon Musk's first trip to space. And I said, you know, we ought to be doing something related to that for making. And chemical engineers weren't getting enough of that. And so I said, I need to come up with a class that would allow people to be able to do that. And I took the Field of Dreams philosophy that if I built it, people would eventually come. And so I said, okay, what research did I want to do? I've been trying to automate tissue engineering for quite a long time, but I had a bunch of students that didn't know all of the different skills that they needed to learn in order to be good at my research. And so I said, my budget were unlimited. How would I go about doing this? And what am I going to do that nobody anywhere else does? Well, believe it or not, in biomedical and tissue engineering, you don't see a whole lot of full mass and energy balance accounting like you do in other engineering fields. And I was able to reinvent myself by applying what I'll call traditional conservation law principles to the field of tissue engineering, use what I knew about how to make things. And now I have my own tissue engineering testbed company that I'm selling bioreactor arrays to a bunch of researchers. And that's how I fund my own research now, so I don't have to go beg for government dollars. And so that was part of my personal inspiration for my making class. But the Kern Family Foundation had some different ideas as to how I should go about putting this together. And they said, you're going to go around to a bunch of different schools throughout the network and pull together a lot of common ideas. Probably the most useful ones that I went to were at Bucknell University. If you have a chance to go to the Bucknell BFAB Maker Workshop, definitely do it. They have a week-long maker and faculty development short course that I went to, and it really changed my career. At that point, I was not good at the CAD drawing or at the electronics part, and very quickly I got to be pretty good at it. I was also inspired by a couple of professors from Lawrence Tech with regard to what they call the quantified self, which had a bunch of biomedical engineering experiments associated with it. So I took what I learned from touring universities across the Keene network, and I came up with the class that you're seeing here. I said, okay, we're going to have a crash course in computer programming, wiring and soldering, a little bit of circuits and a lot of Arduino, a little bit of CAD drawing, a lot of motors, some 3D printing and laser cutting, and some printed circuit boards. And we're going to have to be able to get that done in about half a semester so that by the end of the semester, they've got a meaningful end of semester project that's going to include what I call questions and issue sheets, and other people throughout the Keene network call a question formulation technique, a little literature search that focuses on integrating information, and then an end of semester showcase similar to what you would see for a senior design showcase. And our then dean said, imagine what our senior design projects would look like if our students knew this as freshmen. And I said, you know, if we're going to improve our research output, it's not just the undergrads that need to know this, it's the graduate students too. So I came up with this class. I'm going to switch over now to the Canvas version of what's on this slide. And let's see.
Jim, if I could just interject
Yeah, go
just for a
ahead.
second.
Yeah, go
So,
ahead.
Dr. Brenner sent a list of resources and links. So you should have those in your email inbox. So some of the things that he's referencing now, you can click on and explore yourself as he's talking about.
The slides are all up here. As long as we're doing the aside, this is a good time for that. The second link is to an electronic textbook that all you'd have to do is give proper attribution. The Canvas course that I'm going to show you in just a second is the fourth link. And then below about halfway, there are a bunch of Keen websites that I've organized that are part of this as well. Okay, and thank you for that. That was exactly the time that I wanted to move to that. Okay, so while I do teach a little bit of coding through LabVIEW, the reason I do that is that I discovered pretty quickly that about half of the students had a phobia about computer programming. And what I'd like to find out from all of you there is we're going to do a quick survey at this point, and I'm just going to listen for feedback. Approximately how many percent of your students are not good enough at computer coding?
So 50%, yeah.
Can you hear that?
So
I'm hearing some 50%. That's about
Right.
what I thought too.
Yeah.
And
right. I mean, I find it interesting that there's if they're skilled enough, that's one thing. Confidence, I don't think that we
they
have very many
definitely lack the
students.
confidence too.
Yeah. Oh, really?
I think people lack the skill set and are overconfident and don't know like how deep the rabbit hole is of like, especially hardware stuff like Arduino. Like, there's a lot of students that are like, well, this should work, but they have no idea like how to think like a computer, how it would work.
Right. No, fair enough. I mean, I think of it as the students that I get into my sophomore design class have had.
Okay, so to summarize, about half of them don't have enough computer coding skills. Some of them are overconfident, particularly with regard to Arduino. Is that a pretty good summary?
Yep.
Okay. Well, I said, because this is an interdisciplinary class, I don't expect my students to come in knowing any of this stuff. I'm going to teach a 2-hour crash course in LabVIEW. And the reason I use LabVIEW for this is because it gives them a chance to code graphically. A lot of the students that lack the confidence at computer coding, they see problems graphically. And so if you lay it out like a circuit diagram, they do a lot better. And so I teach a couple of really easy problems of conversion of Celsius to Fahrenheit, both using a graphical approach that looks like a wiring diagram and using computer code. And that helps to get them past the computer code problem. But then I have them do a 6-hour programming assignment where if they've taken a computer code class before, they get through it in about an hour. And if they've never done any coding at all, it takes them about 6 hours. Have them do some wiring and soldering. The heart of the course is 5 2-hour lab sessions that focus on Arduino. many of you have done the blink lab. I then have them do a temperature sensor, a load cell sensor. The load cell, they've got to have soldered the shield first. So this one bundles both what they've learned with regard to Arduino and the soldering, but I have a backup plan such that if their soldering wasn't any good, they can still finish the load cell sensor lab. And then for the pH and the salt concentration sensors, they have to do some calibration. And once they've learned how to calibrate their own instruments, they're ready for a little bit of motor programming. And I have them in parallel do some Python programming once they've finished the LabVIEW programming. And the Python programming is specific to robots. So that when they combine what they've learned about the robots and the Python, then they're ready to tool robots around the classroom. And there's a little competition to see who's the most innovative there. Last year, we had one robot that won that did the cha-cha slide and played its own music. That was pretty clever. If they've never done CAD drawing before, and a lot of the chemical and biomedical engineers I find haven't, there is a tutorial list that was developed by Margot Vigent at Bucknell University that uses a program called Onshape. And her tutorial list here, if the students do the bold-faced exercises in Onshape, takes them about 5 or 6 hours to go through those. And if they went through all of these, it would be like going through a 3-credit freshman CAD course. But they probably only need about 6 hours of CAD in order to be functional. But if they're a mechanical engineer, they probably need to go through the whole thing. But the nice part about this is, if I go to the CAD at the Onshape website, Onshape, it looks and feels like Google Drive for CAD drawing. And the nice thing about it is that their tutorials are essentially idiot-proof. I am not very good at CAD. I'm a little bit better than the students are, but I've had 500 students go through the CAD drawing on this. I've had one student ask a question, and that was way beyond the scope of the course. It was not something that was covered in that training. So it freed me up to do a lot of stuff that I was better at. Then I had some intermediate level experiments about mid-semester. And this one here that involves, it says speaker box. That speaker box, they basically have to solder their own LEDs, do their own wiring. They have to 3D print feet. They have to configure an Arduino to use Bluetooth to play some sort of music. They have to laser cut or engrave the speaker box top. And once they've done all of those things, they're ready for the second half of the semester for their end of semester projects. And I have them do a questions and issues sheet to get their project started. Then I have them do a literature review as part of a group. That's pretty early on. They have to develop the business case. And by about mid-semester, I've got most of the items in that they're going to need to build for the next month. And the hardest challenge with regard to this class is not teaching all of the content. It's actually being the project manager for that many different projects. And yeah, every group has a different project. And one of the key things about this is that I actually have professors recommend projects if they want to get a data acquisition and control system built, or they have something for their research that they want built, sorry. I have them put that as a possible topic at the beginning of the semester, and they get to be the customers. And so I get a lot more buy-in from the faculty so that I don't have to manage every single project. Sorry, I'm just getting over a cold. Okay, back to where I was. I need to get back to sharing here. Okay, so that's most of the content. And in here, I have links to all of the different chapters of the book that goes along with this. Most of the students are going to spend time on chapters 10 and 11, but for the faculty, I'm guessing that chapter 13 with regard to the 12 and 13 with regard to the project management, probably going to be of more importance to them, as well as how to purchase maker equipment on a shoestring budget. We do have some equipment that we paid full price for, but I paid for a lot of this stuff out of my own pocket. And I think that's actually the way to do it in a lot of cases. Now, the keen part of this slide that I'm going to right here is a card deck at the Keen website called the design process. And what I've done is organize this into all of the different things that I think ought to be part of a design project. Why did I come up with this? Well, I got sick and tired of students thinking that the only thing on here that they needed to do was number 21, designing and making the prototype, and skipping all of the important aspects on 1 through 20 that Keen wants us to focus on. And frankly, when I worked in industry, they wanted us to focus on as well. So I organized this in a way that hopefully you can build off of. One thing that I should have said earlier was that we did this partly because our chemical and biomedical engineers weren't getting enough product design at the beginning. They weren't getting enough computer coding or CAD drawing. We decided we were going to bundle it all into one class.
My mind, there are two aspects.
Oops, sorry. Thought I'd gotten rid of all of my audio here. I need to switch back to there. Okay. Systems engineering is the way to teach this kind of stuff. You've got to basically convert all of the entire process or the entire product manufacturing into a set of boxes, as well as your subsystems and your components. And if you think about it, your computer code, your CAD drawing, your wiring diagram, all of those things are going to have the same general set of ins and outs. And the difference between all of the different majors is that most of the individual majors only teach 1 or 2 of these instead of teaching all of them. And frankly, for what I will call the engineer of the future, this is the approach that we need to have our students take. And probably the most important part is to get them to define the interfaces. When you have multiple people or multiple groups working on a project, usually the problems are associated with making the interfaces actually work. Okay, I think, whoops, why is that not going forward? There
So
we
what
go.
I do.
Oh, I forgot to kill that one too. That's why. Okay. In order to make your life a little simpler, I've got a Canvas site and a Google Drive site to organize all of this so that you can manage the projects a whole lot easier and faster. If you've got 15 projects like I typically do for this class, if you don't use these sorts of tools to make your life easier, you're going to drive yourself insane. The hard part is not teaching the class, it's managing that many projects. And for those of you who've taught senior design, you probably know exactly what I'm talking about. The fun part is having the end of semester showcase. I recommend that the students spend at least 2 hours per week in a supervised making environment outside of class time. I have a specific grading sheet that if you ask me for it, I'll send it to you, where they have to, on their own, total up the number and complexity of their sensors, controls, CAD drawings, etc. And I bundle all of that into a curiosity factor. And then I have them do a literature search, a patent search, and a search for sites that are somewhere on the internet owned by companies. And they get a curiosity grade for that. But the real key part here is how they integrate the information. I actually assign triple value if they do an email or a phone call to somebody that they quoted, because what I want them to do is learn from those people, hopefully get a job from them in the future. And I don't want them having to repeat what somebody else has done. I want them to be able to get past that as quickly as possible and move on to what's going to be truly innovative. And then what really excites the students is that I give them $2,000 of Monopoly money, and they are allowed to assign value to each other's projects to simulate customer interest or crowdsourcing. And at the end of the night, they redeem that for Arduino-based sensors, controls, and other items. It's kind of like an adult version of a goodie bag, and they really enjoy that part. And I think that while I do have more slides, that's probably where I'm going to call it for now. And I think I'll take some questions at this point.
All right, thanks, Jim. Any questions? I could repeat them for his.
Oh.
Could you
I guess
repeat
I'll
that?
start, yeah, I guess I'll start with a question, Jim. I'm curious as to how to onboard faculty to do these types of things, right? Like, how do you provide some confidence, some safety net, right? Like, I joke that for some things that I teach, I don't have to actually do the homework I assign to students, which is my saving grace. But how do you what kind of support do you give to individual faculty as they're trying to implement some stuff?
That's a great question. I do have a workshop that I give. I allow faculty to sit in on either individual exercises, or I've even had one faculty member take the class along with the students, so that he was able to improve himself. But one of the websites that I got in the chat is this one that says Making You a Better Maker, Faculty Development Workshop. And it's not a suspicious link. Hold on for a second. It went to, I need to switch this so that you can see it. Okay. So I have a workshop that I give on campus, and I am toying with the idea of having this be something that I offer remotely. Certainly you can download everything at this point, but if you would like to have me organize a workshop like this, I'm willing to do that. Frankly, Bucknell's is better organized than mine is at this point, but I do have a lot more different things than they do. They have more faculty buy-in than I do. I totally understand the fear factor that you mentioned there, Micah, because that was my biggest concern going in was, what if I'm not the world's expert on wiring diagrams or on CAD drawing? How am I going to get past this, that with the students? It's not as hard as you think, but there is a fear factor there. And having the faculty go through a workshop, frankly, it's easier to get them to do that in the summer. But I am going to be doing it with people from local industry over the Christmas break. So I do this once or twice a year for non-students.
Right. All right. Thank you. Yeah. And so that link goes to Engineering Unleashed. And so you need to .com. So you need to sign up for a free account if it's not readily.
Yes, you do need to go to sign up at the Engineering Unleashed website if you're going to go to it. But hopefully that'll encourage more of your people to do that.
Right. Thank you. Cool. So we're just about out of time, but any questions, lingering questions? Sure. So a student asks, what's the workload of this particular class compared to other more
That's a
technical
great
classes
question.
they might take in parallel? Yeah.
It really depends on how much preparation they've had before taking the class. For most students, it'll feel like 4 credits. There's 1 hour of lecture that is common to all the sections, 4 hours of lab, and I split that up into 2 2-hour sections. I'm teaching that, and a teaching assistant is helping me out. I've got 20 students per section for 3 sections for that. Usually by about midterm, I'm mostly doing project management. And so it is a lot of work. The students find that it's about 10 or 12 hours of work per week, but it varies a lot. And it depends on whether they've done any computer coding or CAD drawing before. So if they've never done either of them, then it might feel like a 5-credit class. I encourage them to team up a little bit. If one person is strong at something, then I ask them to help somebody who's not strong at that topic in exchange for a little bit of retribution's the wrong word, but a recompense. They help each other out where they're weak. And that definitely helps in the team building part. Good question.
Sure, thank you. So I think we're about out of time. So let's thank Jim for his presentation and time today. Thanks, Jim.
Thank you. Don't hesitate to email me at jbrenner@fit.edu.
Sure, and we'll circulate the list of resources, and that might be a reference to check into as well. Thanks again, Jim.
Thanks.